Hello everyone, welcome to this problem solving session. I hope you are doing well. So we will start now. So if you have any doubt from last time, just let me know. I will wait for some time, then we will start. So yeah, okay. So let's get started. So let me summarize the this week content. So in the this week sessions would mostly consider the like the non equilibrium. Just wait, I lost my connectivity. Yeah, yeah. So basically, in this week content, what we will consider as the non-equilibrium, like what the special case of like semiconductor in non-equilibrium. How we will create the non-equilibrium? So by injecting some charge carrier. So the charge carrier we can inject in multiple ways. So one is applying bias. So you apply a potential difference to the material, and then applying bias, and then other is you do like you shine a light that also lead to like the photon absorption, and consider corresponding to that like there will be the electron will jump from conduction from valence band to conduction band, and that will lead to current flow in the semiconductor. And typical devices are like the photodetectors and those all the photosensitive devices you see around. And especially and uh, the for bias applying you see all the for diodes and transistors and MOSFETs. Those are we are creating a non-equilibrium kind of situation by applying a bias in those devices. Then like the so when you apply a bias like how the semiconductor is different from the metal. So in the metal only like they have only the carriers are so large, and you just has the diffusion current, and the number of carriers or free carriers per se are so large that you can just model the current or write the current just a very accurately just by just by considering free electrons or free charge particles. That is valid, but that does not explain different like different devices, for example MOSFET and BJTs and those, if you don't consider like the space dependent or diffusion like transport kind of thing. So in the semiconductors, like the metals or typical like highly conductive materials, they have drift current mainly. So here the so they have diffusion current, but drift current dominates more than order of like the order of difference exists in the drift and diffusion current. So and there in the conductors drift current dominates, but in the uh, semiconductors diffusion current also dominate in some part of regions like on the devices, and the drift is always a one of the mechanism. So in this basically that's why we always study like in 10th class when we study metals. So we just study the normal rho equals to rho r equals to rho l by a, and rho we derive just by considering the charge as a free particle. There is no influence of any potential which exists due to the immobile charges which are nucleus in the solid materials, nucleus or inner cores electrons in the solid material. So those consideration we need to take care of in the semiconductors. So so the one of the primary phenomena this discussed in this class is what is normally counterintuitive when you are, especially you are in electrical engineer or you are not from physics background. So basically you apply statistical mechanics to the charged particles and those electrons and holes, and then you calculate the diffusion of those in the solid materials. So that constitute a diffusion current. Also, there was a discussion on the non-uniform doping. Suppose you are creating a gradient in doping, then like how it can be different from the from a like the here the electrons are dispersed, here is the dense. So like what how it will be different from the uniform doping, that was also discussed. And the equilibrium and non-equilibrium carrier response, basically with the light or like the minority carrier injection. So you can inject a minority carrier with two mechanisms. Either you shine a light, for example in photodiode or photodetectors, and you can inject a charge carrier, and especially in BJT or MOSFET, just by applying a bias also. So what will happen? So suppose this host PC of silicon is by dope N type, and you inject shine a light that will generate the electron and hole carriers. Since the electrons are very large in quantity, so you won't see much difference in the electrons or majority charge carriers, but you see stark difference in minority charge carriers. So if you consider the recombination in this semiconductors, so that so at the initial boundary, if you inject charge here, so those charge will so it will get injected here, and it will so as the charge carrier, so now at this interface the concentration is huge. So because you are directly shining light at this interface, as you go down, the charge diffusion will take place. So some profile it will follow. Also, like in when the carrier travels in the bulk of the semiconductors, so what happens, they are they get absorbed. So they get not absorbed, they get recombined with the electrons or the or holes in this in the semiconductor. So basically you need to consider, like the one is the diffusion of charge carrier, diffusion of mainly minority carriers, and other is the generation recombination. So you can have some generation also or recombination also. Some carrier can recombine and then leach. So that leads to gradient in doping, gradient in charge profile, and that can be considered like kind of creating a doping gradient or those kind of. So those are the different mechanisms. So other example, and this is the minority carrier diffusion equation, and you can drive the diffusion equation. So you can drive so the total current in the semiconductor. Suppose for example uh, for electrons, so the total current due to electrons is Jn is Jnd is the diffuser current density due to the drift, and Jn diffusion is the current density due to due to diffusion, and that is the similar that is the nq mu n plus mu p. So if you consider total and applied field, plus the diffusion is because of the concentration gradient. So basically this apply q dp by lp. I think I qualitatively right, I don't remember this expression. So this is and you create the gradient. So this is dou p by dou x. So this is due to diffusion plus due to electrons. So the sign you need to take negative because electrons and hole travels in opposite direction. So that you need to take plus q dn and LP divided by dn by dx. So basically, you need to take so this ln is the diffusion length. So what is the diffusion length? So diffusion length is the suppose electron is traveling in a piece of semiconductor. So before recombining, it travels up to a certain distance. If you can count large number of this incidents and take the average, so that is known as the diffusion length. So that the definition of the diffusion length is uh, sorry, just I don't know. Sorry for disturbance. My net is bit naughty. Okay. So then, like the diffusion length is basically the average distance. Average distance. So average distance. A carrier distance. A carrier travels before recombining actually. So suppose like this electron goes here and then recombine and just so you calculate basically average of all those distances, and that is known in the diffusion. Also like few more important concepts in this, like for example when you are in the equilibrium, so you have one Fermi level EF. So in the non-equilibrium case, you can consider a quasi Fermi level. Why this call is a quasi Fermi level? Because you define a Fermi level in equilibrium only. But quasi Fermi level case, you you assume that the generation and those things are not that high, so that those approximately equilibrium statistics is valid in this case. So there you define the two Fermi levels. So for equilibrium, so the electrons and hole Fermi levels are equal. So En equals to Ep equals to EF. But in the non-equilibrium case, suppose you shine light or inject carriers somehow by applying bias, then those EFN and EFP separate. So now the whole Fermi level and electron Fermi levels, so EFN and EFP. So those Fermi levels are known as the quasi Fermi levels, and you can go through the lecture slide to have more discussion. And also like some process related discussion was also there in the class. So basically how you fabricate the devices, so it's like similar to like the way you construct a high rise building. So like you basically like deposit and remove the material. So basically you add and remove the material. So suppose you are let's say this is the cross section and this is the area. So suppose you want a diffusion, so then you create a selective area and then you cover other area on mask, and then you do selective process, and this in the cross section it will look like this. So then basically you do like the whatever doping and other doping and like diffusion and those process in this, or etching you. So this process you keep repeating and keep building other layers, and that you do it with the, so normal starting is your silicon wafer or whatever wafer you are using, and you keep adding the process, or adding or removing material will follow those steps. So yeah, so that was the quick overview of the content discussed in the class. So if you have any doubt going further, you can ask. I will wait, pause for some time, and then we will carry on this solving session if you don't have any doubt. Okay, the first problem talks about. So this was one of the gate problems. Consider a silicon sample with maintained at 300 Kelvin. So this is operating at room temperature. And the schematic of energy band diagram is illustrated as shown in figure. Consider EF as a reference energy level. So the question is asked, so in this structure, does the equilibrium condition prevail? So you need to find by looking at this diagram whether this semiconductor is in equilibrium or not. So we may confuse by seeing this band bending is there. So the and like conduction band and valence band are not or flat. So we may assume this is not the equilibrium. So that may not be the case. So ideal condition for equilibrium. So that so the condition for the equilibrium is your df by dx, def by dx should be 0. So that is the condition for equilibrium. So we are not talking about the quasi equilibrium, because like that also you can in some approximation you can consider as a quasi equilibrium only. So this, see, like this band is flat, like this Fermi level is flat. So that is the ideal way to test whether the semiconductor is in is in equilibrium or not. And like the other like people get confused. So here this the band bending is there. So the conduction band at each location is varying, and the same as valence band. So people may think that this can be considered as a non-equilibrium case, but it is not so actually. So this kind of banding can exist if you consider a charge gradient. Actually, if you consider a so if you apply a the charge gradient, so then if you apply a not charge gradient, if you apply a uniform charge in the semiconductor, or if it is a depleted of carriers actually. So if you remove electron from the semiconductors, and then you will see only immobile charges in the those state field. The typical example of this is your space charge region in PN junction. So I am going little bit further. So basically, what happens is in the PN junction, in the equilibrium, Fermi level remains flat, but even then you have this bending of within the this junction region. There is a bending of the conduction and valence band. So the ideal test. So for example, if you can see here, so although even in equilibrium does this bending exist, but you can't you consider until unless this Fermi level is not varying, then you can consider this as a equilibrium case only. So that is the idea. So here also in the depletion charge region, so that's why you call it the depletion charge region. So you remove all no, some of the mobile carrier from this region, and this region is depleted of charge carrier, and that is so here there is a band is not flat, but this is in equilibrium. So is the case is given here. So the correct option is uh, no, because of the energy EC and EV are banding, so this is wrong. Yes, because energy difference between EC, EV, EI and same, this is also not correct. EI and EC band difference always remains same. EC and EV also remain same until unless you do different thing or you do some extraordinary thing. Yes, because the Fermi level is constant alone. So this is the correct answer, and this is the correct explanation also, because the Fermi level is flat, so that's why your semiconductor is in equilibrium. And the last option is no, because EF is not parallel to EC. So EF may not be parallel to EC in all the case, whether is equilibrium, non-equilibrium. So EF you need to see it properly. So that was this question. If you have any doubt, then you can ask. I will pause for some time, and then I will move to next problem if you don't have any problem. If you don't have any doubt. Okay, so let's move to next problem. So the sketch of the electric field is uh, inside the silicon as a function of x is given by. So this was the same as previous. So this was related to diagram 1 and 2. So the same diagram. And to know the electric field quickly, like for example, principle, it is the slope of. So basically, electric field, you know, it's minus derivative of potential, negative derivative of potential, and you can write the potential by energies. So V is simply E by Q. This is very simple explanation, and that with respect to the conduction band and valence band, you can calculate potential with respect to this band offset, and you can calculate, like if you put this, then you will find like that E electric field is basically 1 by Q times dE by dQ. Or and since you are considering the the negative charge, and then you need to take one extra charge because of the Q, then this will become positive actually. So yeah. So so then like this you will see this basically, so for that case, so basically to get the electric field, you need to divide scale by 1 by q, and then the dE by dx you need to calculate. So basically, since conduction band EI and EC are remain fixed with respect to each other, so you can take any of those bands. So basically you can calculate 1 by q dEc by dVx, or 1 by q dEv by dx, or 1 by q dEi by dx. So that is the case. So like to calculate. So now in this problem, this the slope is, this is a straight line. So the this straight line you can see by y equals to mx plus c. You can model, and this in case of straight line, this remains, solo slope remains fixed actually. M is fixed. So this, if the m is fixed, so your slope dE by dx is fixed. So that's why your field is fixed. So the electric field is constant in this case, and that is and since this slope is positive value, so the electric field will be positive. So yeah, so let's see the option. So A is given as the one of the possible options. So the electric field is constant and it's positive. So this may be the correct option. And the second one is the E is given as negative. So but in this, so basically like to consider like the the uh, 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 like to consider like what is the slope, you either you can calculate which side it's bent. So this side you can see this line has a positive slope, that means your electric field is in the positive direction, and other options are linearly varying into positive direction, and other is positive but linearly decreasing, other is increasing in the negative direction. Both the options are wrong actually. So this is the correct option is first one. Uh, so this is the correct option is that the your electric field remains flat in this region. So yeah, so if you have any doubt, I'll pause for some time and let's just move ahead. Yeah, if you okay, so let's move to next problem. So yeah, so a sample of semiconductor has a cross section area of 1 centimeter square and thickness of 1.1 centimeter. So let's see, like if we draw this, so this is the semiconductor. So this is the semiconductors. So this, if you draw, so this is thickness is given. So this is 0.1, and this cross section area this side is given as 1 centimeter square. So what is the volume of this? Volume is we can calculate as the 1 centimeter square multiplied by zero point 0.1. So it is 0.1 centimeter square is the volume. A number of hole pairs are generated. So a number of electrons hole pairs are generated per unit volume per unit time by uniform application of 1 watt of light at the wavelength of 630 nanometers. what is the approximate steady state carrier access concentration? Uh, and if the minority access carrier lifetime is 10 microsecond. So this tau is given as 10 microsecond. So what will happen? Like this case basically you are eliminating. Uh, so in this case, basically uh, you are eliminating this piece of semiconductor with the uniform in the throughout the bulk. So all the photon absorbed within the semiconductors are uniformly like generating electrons here or uniform. But ideally, like in most practical devices, this kind of scenario does not exist. There is a absorption profile, or like that profile varies because of different material parameters. So that may not be the case, but this is hypothetical case. So we consider the uniform excitation case. So uh, as Yeah. So this case, the carriers are eliminated uniformly. So we will so the generation and recombination will taking place uniform throughout the sample. So the generation rate G is given as delta n by tau. So then basically, and the assumption is that assume each photon created one electron pair. Experimentally or in the practical case, this does not happen because the whatever the photon you science that may absorb that may either get through the material. So suppose this photon is not getting absorbed, it will pass through this semiconductor or piece of semiconductor, or it may absorb but does not generate any electron pair, whole pair. So there are inefficiency involved in most practical devices, but this case here we are assuming that each photon will generate an electron hole pair. So so basically, from the power we can calculate how many. So power is 1 watt, and what is 1 watt is like 1 joule of energy per second falling on the line. So 1 joule we can convert in the electron volt. So then it we need to multiply with the 1.6 into 10 power 19. So if we multiply by uh, uh, so uh, this uh, so we will calculate the how many like how many like this is the we can calculate how many electron volt 1 into 1.6 into 10 power 19 electron volt per second. So no, this is 1 by 1, 1 is to 19. So this will be 1 by 1 into 1.6 into 10 power minus 19 electron volt per second. So this will come as a electron volt. Uh, no, no, no. Just, yeah. So this many number of uh, yeah. So this much, uh, and then what we need to calculate the like how much is one photon energy is. So we can calculate that by just from the wavelength. So this E is basically 1.24 divided by lambda of in micrometer. So we are given as 630 nanometer. So the energy is given as 1.24. This is 630 into 10 power minus 3, and it will become 1.24 divided by 630. So this is 0.63, uh, and into 0.63, and you will get around 1.9 electron volt something. So so the energy in the joule is 1 upon 1.6 into 10 power 19 on the denominator electron volt per second. So to get and the energy of one photon is this one. So to get the how many number of photons in this much energy rate are there, we need to divide by the energy in electron volt. So if we divide that, so the photon rate phi is equals to 1 over 1.9 into 1.6 into 10 power minus 19 photons per second. So this was in electron volt, this was in electron volt, and we are dividing this by the unit of one photon, and then we can get how many number of photons per second are falling on the semiconductor. So that we will if we will solve, then it we will get 3.17 around into to 10 power 9 per centimeter cube per second. So this because and yeah, so right now this is not per centimeter cube, this many power is falling. So we can calculate how many like these are the total number of so these are the total number of photons falling on the semiconductors, and because the assumption is that each photon generates an electron, so these many number of electrons are getting generated in the semiconductor. So this is this is just this will be 20. So this is 20. So now to get the this number many number of photons per second, and to get the how many number of photons per unit volume we need, we can calculate how many number of electron the whole pair per unit volume is getting generated. We need to divide the volume of this semiconductor with the this. So this will get 3.17 multiply by so no, this is 18. So into 10 power 18 divided by zero point 0.1, and if you take this up, you will get 3.17 multiplied by 10 power 19 per centimeter cube per second. So per unit cube per second, this many number of electrons or pairs are getting generated, and then with this we can calculate the so two. So this is the per second, and so this is the generation rate we got, and to calculate the excess concentration, we need to multiply this by tau, because like the number of electrons or pairs are getting generated in an average, how many number of electrons hole pairs are there is determined with this tau, and if we multiply with this tau, then it's like 3.17 into 10 power 19 multiplied by 10 power minus 5, because tau is given as 10 power minus 10 microsecond, that will be equal to 10 into 1 10 power minus 6 second. This will become 10 power minus 5 second. So this will become 3.17 into 10 power 14 per centimeter cube. So the correct answer is the third one, and this is the correct answer. So is that clear? If you have any doubt, then I will pause for some time, and if there is no doubt, then I will carry forward. So the next problem talks about approximate the approximate thermal velocity of electrons and hole in the at in silicon at room temperature is how much times 10 power 70 meters, and assume that electron effective mass is 0.26 times m naught. M naught we generally take as the free electron mass, which is 9.1 into 10 power minus 31 kg. So that we need to calculate, basically just equate the thermal energy by the, so in the room temperature with the thermal energy is given as 3 times half of kT, and this half of kT is the room temperature thermal energy, and this three factors comes because of the 3 degree of freedom. So electron can move in three different directions, so that comes from that degrees of freedom, and that we need to evaluate with the kinetic energy of the electron. So if we calculate, then we can get V as so this half will get cancelled, 3 kT by m star, and then this will is square root, and we will get velocity as 3 kT by m and square root, and that if you put the value, the kT is like at room temperature it's 25 milli electron volt, and you can convert from milli electron volt to joule, and then you can calculate the velocity. So the final velocity you will get around 2.3 into 10 power 7 centimeter per second, 3 something. The correct answer will be 2.3 into 10 power centimeter. So this was a state formula substitution kind of question. Okay, so let's move to next section. So so in a very long p-type silicon bar with cross-sectional area of this, Na is given as this. So this is acceptor is doping is there. So this is p-type semiconductor. The holes are injected such that steady state excess hole concentration is 5 into 10 power 16. So this is no, this is n type. Yeah. No, I think yeah, yeah, it's given as p type. So this is p type. So this is given as p type. So this and holes are injected in such that the steady state hole concentration is 5 into 10 power 16 at x equals to 0, and the mu p is given as this. What is the diffusion length LP? So basically, for a long semiconductor, so the distance here is given as long p-type semiconductor. So basically, we need to consider a long case profile, and then like there basically the excess p-type carrier is your excess carrier is your d p naught, time exponential of minus x by lp into dp. So x by square root of x by square root of lp, and uh, lp is given as square root of dp tau p, and that like this is the characteristic length, and you can calculate how many number of excess carriers are generated. And then if you basically in this question we need to calculate what is the value of dp, we need to calculate what is the value of lp. So lp is square root of dp times tau p, and dp from the Einstein's relations you can write mu p kt by q times tau p, and this if you put this then this is 500 in times 0.026 into 10 power minus 10 times 3.6 into 10 power minus 5, and then basically if you calculate what is the diffusion length in micron, if you calculate with this number you will get around 0.36 micron length. So the correct answer will be C option, and which is 0.36. No, no. This is not 0.36. This is 36. So correct answer will be 36 micron, which is the C option. So the this will be 0.36 centimeter, but it is 36. No, no, not this 36 centimeter. So it is 0.36 into 10 power minus 4 minus. This will come around 3.6 into 10 power minus 5. 3.6 into 10 power minus 5 centimeter. That you convert into the micron, and then you will get the value. So this will come as a 3.6 micron, and so no, just wait, I think it should come 3.36. No, this is 0.36. So this is 0.36. The correct answer is B1. So the final answer is 0.36. No, yeah. So the correct answer is 0.36. So yeah. So if you have any doubt, then I'll pause for some time, and yeah. Okay, so let's just move to next problem. So next problem, it is asked, consider a n-type semiconductor with a non-uniform doping. Uh, with a non-uniform doping, Nd is given as this. L at L equals to this. Determine the induced electric field. So basically, like the doping profile is given as the exponential. If you consider the potential variation in this region, it will be linear actually. So then you can consider and then you need to take the slope of that, and you can calculate by the slope, then you can calculate the concentration. So so the electric field is given as the electric field is given as the epsilon is given as minus kt by q times 1 by nd times nd derivative of nd with respect to x. So basically nd, this is the doping concentration, and this is the your your slope. So basically we can calculate the slope at x equals to 0. So then if we calculate the slope, so this d dnd by dx from this equation if we calculate, then it will become 10 power 16 times exponential minus x by L. And this again we need to take derivative, then this is minus 1. And then if we put at x equals to 0, so x equals to 0, then this exponential term goes off, and it will become this is 10 power 16 times minus 1 by L times. So this is nd is 10 power 16. So this we can bring down to the bottom, and this will become 0.026 electron volt times 1 by L, which will become 0.026 divided by 200 micron, and that you will get around this is electron volt, and then you can get with this kT by Q is in the volt, and this bottom unit is in the unit of dimension. So the dimension is around, the value you will get around 1.3 volt per centimeter. So upper unit in volt, and this is 200 micron. This we can convert into centimeter, and then you can calculate the final answer in centimeter. So the correct answer you will get is around 1.3. So the correct answer will be 1.3 into 1.3 volt per centimeter. So if there are any doubt in this, then we can have. Okay, so let's move to next. So the energy band diagram of a semiconductor is shown below. Uh, so this diagram is shown like the typically characteristic is this is NPN type BJT. So this is NPN. So how you will identify, like, see, no, this is PNP. So this is PNP. So this is side is collector side. This, so the in BJT the emitter is heavily doped. Heavily doped. Collector is moderately doped. And yeah, so the collector is moderately doped, and base is kind of moderately doped or low doping compared to this. So then basically like then if your like the emitter is p type, then the Fermi level will lie closer to the valence band, and the in the collector side, the also p type, the Fermi level will lie closer to the valence band, but this Fermi level is different compared to this. The emitter size is heavily low, that's why like the Fermi level lies very near to the conduction band, and the in the collector case it lies bit far away compared to the computer, the emitter region, and the base region is n type though. So this conduction band lies closer to the to the valence band. So basically, so this is the example of PNP type transistors. So let's just answer a few questions based on this. At this position x1, what is the type of semiconductor? So the x1 is given as this. So this is, so basically you can see at here at this cut line, basically the Fermi level lies closer to the conduction band. So it is basically n type. So it is n type. So the correct answer is n type. At position x2, what is the kinetic energy of electron in electron? Kinetic of energy of electron in red. So basically in the band diagram picture, if you see, the band is basically the minimum kinetic energy position. So here if you draw the band band branches or band structure on the top of this, then electron will have this minimum energy plus some kinetic, some energy, all the states which are being occupied. But since the electrons here is shown in the just at the edge of the band, so it is the kinetic energy equals to zero position, and full is uh, uh, and the only the energy is the potential energy which a electron sees. So the correct answer will be the kinetic energy will be 0 electron volt. So this was this question, and let me. If you have any doubts, then you can ask. I will pause for some time. Okay, let's just move to next problem. Let's just move to next problem. Based on the Venn diagram, which of the following describe the approximate electric field versus position? So, yeah, so this was the for 7 to 9 problem. So again, we need to follow the same diagram. So let me draw it approximately here. So this is valence band. This is conduction band here. This is this lies closer. So similarly, you can draw conduction band here. Yeah, so this is the band diagram picture. So basically, to get the electric field, you need to take slope of this either of the band edge. So you can take the slope of either EC. So this is EC, this is EV, and if you draw EI also, in this structure EI is not drawn. So you can take slope of either EC or EV. So the slope, let's just start calculate. So this line is flat actually. So if you take 2 point on this line, the slope is 0. So the initially the slope is 0. Then let's just start plotting also. So let's divide in this into some regions. So let's say what's in each region the profile will be. So now uh, the this up to here the slope is flat, so the electric field is just directly proportional or is directly related to slope of the conduction band or valence band, so it will be also be 0. Now as we move in this region, the electric field will start, this slope will start become negative. So then this field will start become negative, and after certain time it reach negative peak where this the maximum is reached. That point it's maximum. After time, this after that this slope start reducing and is still negative. So this will get start reducing up to here, and then after this the slope again will become flat. The curve again will become flat, and the slope is 0. Now after this the slope is positive. If you draw the tangent on this each point, you will see the tangent is have the positive slope. So the slope will have positive, and as we increase further, the slope will get decreased, and finally it will become 0. So it will peak at the maximum, and finally it will become 0. So the correct answer as per this picture is A answer, where the electric field looks like two spike. One is the negative direction and other is in the positive direction. So ideal way of calculating this is just by looking at the slope of the conduction and valence band edge. And this slope is fairly Simple thing. Yeah. Yeah. So this was this problem. So so yeah. So let's move to next problem. If you don't have any doubt in current, if you have doubt, then ask. I will pause for some time. Okay, then let's move to next problem. So, consider a long rectangular bar of direct band gap P-type semiconductor. P-type semiconductor. The equilibrium hole density is 10 power 70. So, P concentration is given as 10 power 17. Uh, uh, and the intrinsic carrier concentration is 10 power 10. So, Ni is given as 10 power 10 per centimeter cube. Electron and hole diffusion lengths are 2 micron and 1 micron. So LP is 2 micron and LN is 1 micron. Electron and hole. No, this is reverse. This is electron and this is hole. The left side of the bar. The left side of bar at x equals to 0, so this is kind of a bar and this is x equals to 0, is uniformly illuminated. So here this illumination is done. Uniform illumination is done with a laser having the photon energy greater than band gap of. So E is larger than Eg, which is larger than Eg, which is equals to 1.1 electron volt in case of silicon. Larger than the band gap of semiconductor. Excess electron hole pair generated only at x equals to 0. So only at this interface are excess hole are generated because of the laser. The steady state electron density at x equals to 0 is 10 power 14 per centimeter cube. And due to the laser illumination, due to the laser and under these conditions, ignoring the electric field, the closest approximation of the steady state electric field density at x equals to 2 micron is how much? So steady state electron density, not field density, is steady state electron. So basically, we need to calculate the electron density at n at x equals to 2 micron. So what will be here? So let's just calculate like what is the inherent number of electrons in the semiconductor. Let's say you don't shine the light. So since this in case of equilibrium, n into p equals to ni square, and then you can calculate number of electrons as ni square by p, which is equals to ni square by nd, and then you can calculate this with 10 to the power 10 square divided by 10 to the power 17, which will become 10 to the power 3 per centimeter cube. This will become. Now since the laser illumination you are doing, this 10 power 14 number of electrons per centimeter cubes are generated, and as they uh, as they diffuse through the inside semiconductor, they will get recombined and they will follow this kind of profile if this piece of semiconductor is long. So the profile which we have solved in the class, the electric steady state electron density is given as is delta n at 0 times exponential of minus x by lp plus delta uh, so yeah, so this is uh, ln. So this is ln, and then basically we need to calculate the closest approximation. Majority carrier, see, like the excess majority carrier we can neglect because inherent this is 10 power 17. So if you add 10 power 14 wholes to 10 power 17, then it won't take much, create much difference. So we can take assumption that whole density remains same, and we need to calculate the electron density in there. So this delta n naught we uh, calculate. So delta n naught is basically this density n of 0 minus n naught. N naught is the equilibrium current, equilibrium carrier concentration minus x by ln. So uh, so uh, this is this is 10 power 14. This 10 power 14 minus this is 10 power 3, and we can neglect this 10 power 3 with respect to 10 power 14, and exponential of minus x is 2 micron. So minus 2 micron, and this is ln is given as 2 micron. So this 2 micron, this will become exponential. So this will become 10 power 14 exponential of minus 1. It will be around 63%. So this exponential of minus 1 is point. This is point. So this will become 0.63 times 10 to the power 14 per centimeter cube, and this will become, no, yes, uh, yeah, no, this is 37%, not 1 minus exponential of minus 1 is 63%, 0.63, and this is 0.37. So this will become 3.7 into 10 power 14 per centimeter cube. So this is the profile, and the final answer you will get around the A answer is the correct. So that's how you calculate this answer. So if there is any doubt in this, you can ask, or you can any doubt if in previous session if you have, then you can ask. I can clear those doubts, and then I hope this is clear and legible to all of you. So if there are no doubts further, so let's close this session then. If you have any doubt in time, let's just please let me know in the next session related to the content covered. So I would like to say thank to you. I hope it is clearly understand. I hope you understand at least some of the things whatever I have tried to convey. So till then, thank you so much for listening, patiently listening this, and we will meet the same time next week on the same time at the same platform. Till then, bye. Have a nice day, a nice weekend, and have a nice time. Thank you so much, and bye bye.